Hello there, Mr. Sutton bringing you the BC Calculus Quiz 2 review solutions for Chapter 6, this topic being motion and accumulation with rate in, rate out. For this problem, we have the acceleration of a particle along the x-axis given as a of t equals 6t minus 2, and they're telling us the velocity is 25 when time is 3 and position is 10 when time is 1. Based off all this, they want the position function. So unfortunately, we can't go all the way from acceleration down to position in one step. We first need to find the velocity function based off of this information, and then we can use that to find the position function. So to go from acceleration to velocity, if you just want the function and not an actual value, you need to use diff-EQ math. So I'm going to take the antiderivative of both sides here. I'm going to get a plus c constant of integration, and then I'm going to use this initial position, time 3, velocity 25, to figure out the c value. So first step, antiderivative of a, that's going to be v of t. And then over here, 6t, that bumps up to a 2 for the exponent. Dividing by that, we have 3t squared minus 2t plus c. So they told us when time is 3, velocity is 25. So I can plug in 25 for v of t, and then I'll plug in 3 for all the t values on the right side of the equation. So on the right side of the equation, we have, let's see, this is 27 minus 6 is 21, plus c. If we subtract 21 from both sides, we get a c value of 4. So then I can rewrite my velocity function as 3t squared minus 2t plus 4. Now we're going to try to turn this velocity function into a position function. So I'll start just like I did up here by taking the antiderivative of both sides. On the left side, we've got x of t. And on the right side, this is going to be, let's see, that bumps up to a 3. Dividing by that, we have t cubed minus, this is going to be t squared plus 4t plus c. And now we'll use this initial position of 10 when time is 1 to figure out the c value. So I can plug 10 in for x of t. And then all the t values on the right side are going to be 1s. So we have t cubed, so 1 cubed minus 1 squared, which is just going to be 0, plus 4 times 1. So when the dust settles, we just have 4 plus c on the right side. Subtracting 4, I get a c value of 6. And plugging that back in, I now have t cubed minus t squared rather, plus 4t plus 6, which gives me answer choice C.
For this calculator-based free response question, we have a particle moving along the x-axis with a velocity given by this v of t function. And we're told at time 0, the velocity, the particle is at position x equals 1. For the first part of this problem, they want to know the displacement of the particle from time 0 to time 3. So if we're finding displacement, that's just the total change in position. Since velocity is the rate of change of position, we just need to take the integral of this velocity on the interval that they're talking about here. So we literally just need to do the integral from 0 to 3 of v of t dt. And this is a calculator question, so we're going to go ahead and actually put this in the calculator. So let's start by putting in v of t into Desmos so that we can use it for this and all the other problems. So we got negative t plus 1 times the sine, parentheses, fraction, and then we've got t squared over 2. Now to do this integral, that'll be int from 0 to 3, and then we have v of t dt. And rounding it to the nearest 3 decimals, that comes out to negative 2.197. And they didn't give us units, so we're not going to give them any units. For part B of this problem, they want the position of the particle at time 5. Since we know the position at time 0, we can just take that initial position, 1, and add to that the total change in position between times 0 and 5. So that means we're just going to add the integral from 0 to 5 of this velocity function. And let's go ahead and do that on Desmos. So I don't need this integral right here anymore, but let me just do 1 plus integral from 0 to 5 of v of t dt. And that gives me the new position at 0.3097, so we'll call that 0.310 if we round it to 3 decimals. For part C, they want the total distance traveled by the particle from time 0 to 3. So for this, we just need to take the integral from 0 to 3 of the absolute value of the velocity. That will ensure that all those little distance strips are counted as positives and there's no negatives mixed in. So integral 0 to 3, absolute value of velocity, v of t, dt. Back to Desmos we go. So we've got integral 0 to 3. And in here, let me do my little absolute value vertical bar. V of t goes inside the absolute value, dt goes outside, and we end up with 4.334. For part D, to get average velocity from time 0 to 3, we just need to use our average value formula. So that'll be 1 over b minus a, in this case 1 over 3 minus 0. And then we need the integral from 0 to 3. And what are we going to put in there? Well, whatever we're trying to average. In this case, that is the velocity function. So v of t dt. Plugging that into Desmos, we've got 1 over 3, and then integral 0 to 3, and then just v of t dt, no bells and whistles in there. And that comes out to negative 0.732. For part E, we want to know if the particle is moving toward or away from the origin at time 5. So to figure this out, we just need to figure out the position and the velocity. If those have the same sign, then we're moving away from the origin. If they have different signs and are working against each other, then we're moving toward the origin. So we need x of 5. And you might remember from part B that that was 0.310. We actually already found that. So that's positive. And now we also need to look at v of 5, so I'll go to Desmos for that. V of 5, just plug it right in there. That's 0.398 approximately. Also positive. Since x of 5 and v of 5 have the same sign, that tells us that our particle is moving away from the origin. It's on the right side of the y-axis, and it's moving further and further to the right. For this calculator-based free response problem, we have some mosquitoes on a tropical island. For times 0 to 31, we have this r of t function that's telling us the rate of change of the number of mosquitoes. And there's 1,000 of these on the island at time 0. We want to know for part A, or actually they want us to show that the number of mosquitoes is increasing at time 6. Okay, well, the number of mosquitoes, the rate of change of those is shown by this r of t function. So we just need to plug 6 into r of t and show that it comes out to a positive number. So let's put r of t into our calculator. So I've got r of t equals 5 sqrt, square root of t, and then tab out of there. And then we've got cosine, and we'll do a parentheses, t divided by 5, and then close that. And then again, we're going to be doing just r of 6 to figure out, the sign of this thing. So if I do r of 6, that's coming out to about 4.438. That is a positive number. This shows that the number of mosquitoes is indeed increasing at time 6. For part B, at time 6, they're asking if the number of mosquitoes is increasing at an increasing rate or increasing at a decreasing rate, with a reason. Well, this one's going to be pretty quick. We just need to figure out the rate of change and see if that's positive or negative. So basically, we're just figuring out r prime of 6. Now, since I'm just taking the derivative at a single value, I don't actually need to figure out what r prime looks like algebraically. I just need to plug in r prime of 6 on the calculator with r already entered in there. So going back to Desmos, let me, instead of doing r of 6, I'm just going to do r prime of 6, and that comes out to negative 1.913. The key here is that that is negative, less than 0, so that tells us that we are increasing at a decreasing rate. For this problem, we want to know how many mosquitoes are on the island at time 31 to the nearest whole number. So we haven't really actually had a function yet to describe exactly how many mosquitoes, just the rate at which that number is changing. So I'm going to define a function. I'm going to call it m. m of t will represent the number of mosquitoes at time t. So now m of 31 in this case, we have to take into account the 1,000 mosquitoes that we started with, so let's make sure we don't forget about them. But then we have to add the total change in mosquitoes from time 0 to 31. So that's going to be the integral from 0 to 31 of this r of t function. And now we'll just do this directly in the calculator. So we've got 1,000 plus integral int 0 to 31, and then we're doing r of t dt, and that rounds off to 964 mosquitoes. For part D on this, to the nearest whole number, they want the maximum number of mosquitoes between times 0 and 31, with some analysis for that. So what we're going to do is we're going to find some critical values for our m function, whose derivative is this r of t function. So I'm going to start by graphing out r of t and seeing where r of t changes. Well, since we want the maximum number, we want r of t to change from positive to negative. We're not really interested in other critical values because plateaus and local mins, those are not going to give us the absolute maximum ever. So going to Desmos again, I can get rid of this stuff here. I don't really need it. So we've got, let's see, here's what our function looks like initially. I'm going to change the window so we're going from 0 to 31. In fact, let me make this -1 to 32. There we go. We can see a little bit more. And there's one spot where we're changing positive to negative. It's this spot right here. This happens at 5 pi over 2. So there was a graph. And this again happens at time equals 5 pi over 2 only. So at this point, because we have not one but two critical values, even though the other critical value isn't one that we want, because there's more than one critical value, we are forced to do the candidates test to figure out the max. We can't just assume that this 5 pi over 2 is the maximum value. So let's go ahead and we've already got our critical value, we've got our endpoints 0 and 31. We're just going to plug all of those into that m function that we came up with on that last part of the problem. So let's do m of 0 first. We actually don't need to do anything fancy for that. That's just the mosquitoes at time 0, which we saw was 1,000. They gave us that. To do m of 5 pi over 2, we're going to need to do the 1,000 mosquitoes plus the integral of r of t from 0 to 5 pi over 2. And let me plug that in the calculator. And let me just move this so that I can see what I'm actually plugging in. All right, so we've got 1,000 plus integral 0 and then 5 pi pi divided by 2, and then r of t dt, and that's about 1,039 and some change. And that's a little bit higher than the 1,000 there. So far this is our winner, but we also have to take a look at 31. Now we actually figured out m of 31 on the very last problem, part C. Remember that value was 964, which is lower than any of these. So comparing all of our answers, it looks like 1,039 is the maximum number of mosquitoes, and that happened at, again, 5 pi over 2 days. But they didn't ask for the days, they just asked for the mosquitoes. On this calculator-based free response problem, we have a water tank at Camp Newton. Of course, it's Camp Newton. Camp Leibniz apparently didn't get a water tank. This holds 1,200 gallons of water at time 0, and during the interval 0 to 18 hours, water is pumped into the tank at this W of T rate here, in gallons per hour. Now we also have water being removed from the tank at this R of T rate, which is another one of these crazy squared trig functions. For part A, we want to know if the amount of water in the tank is increasing at time 15. Why or why not? So one way to do this would just be to plug 15 directly into W and R and compare those. If the rate in W is higher than the rate out R, then we would say yes, the water amount is increasing. But I did a little bit more on this one. I actually chose to define a new function. I'm going to call it G. G of T is going to be the water in the tank. and then G prime is going to be the change in the water in the tank. I'm doing this because this is a multi-step sort of free response problem, and I know I'm probably going to need to know about the water in general later on in the problem. So I'm just planning ahead here. So G prime, the change in water, that's going to be rate in minus rate out, so W of t minus R of t. And what I'm going to do is just plug 15 into G prime and see if it comes out positive or negative, to see if the water has a positive or negative rate of change. So let me go to Desmos and enter a few things in. So let me start by putting W of t in there. Again, that's 95, and then we have square root of t, and then sine exponent 2. This actually works on Desmos. And then parentheses t divided by 6. Great. We'll also do R of t. That is going to be 275 sine squared t divided by 3. And then my G prime I'm actually going to enter as just lowercase g of t. That's going to be W of t minus R of t. And if I plug 15 into that, I get about negative 121.090, and that's gallons per hour. Since that's negative, that tells us the amount of water is decreasing at 15, not increasing. For part B, to the nearest whole number, they want to know how many gallons of water are in the tank at time 18. So I'm looking for G of 18 based on that function I wrote earlier. To figure that out, I'm going to need to take the initial 1,200 gallons that were already in the tank, and I'm going to have to add to that the total change in gallons from time 0 to 18. That's going to be the integral from 0 to 18 of my G prime function that I wrote earlier. Let me do all of this on the calculator now. So we don't need G of 15 anymore. What I'm going to do, we're going to do 1,200 plus integral 0 to 18, and then instead of G prime, I had this in here as G, so G of t on here, dt. And if we round to the nearest gallon, that's 1,310 gallons. For part C, they want to know at what time between 0 and 18 is the amount of water in the tank at an absolute minimum, and then show the work for that. So what I want to do is find some critical values using my G prime function that I created earlier. That's again telling us the rate of change of the water. So I'm going to figure out, since I want an absolute min, I'm going to look for places where my G prime goes from negative to positive. I'm going to look for local mins, and I'll use those as critical values. So G prime changes negative to positive, where exactly? Let's go to Desmos and find out. So I've got, I don't need this in here anymore. So W and R, I'm going to deselect those so I'm not graphing those. And instead I'm just going to take a look at G of t, and we'll make the window be from 0 to 18. Actually, let's make it negative 1 to 20, just so I see a little bit beyond what I'm looking at. And I kind of see where things are crossing here, but it's sort of hard to tell the direction that they're going in. So let me adjust my window a little bit more. Let's make my y-axis go by, I don't know, let's try 80 to negative 80 to 80 and see what we get. All right, I have a little bit better picture now. I bet I could do even better, though. Let's make this like negative 200 to 200. And that's almost perfect. Zoom out a little bit. All right, so if I'm looking for negative to positive, let me select my function that I'm trying to do that for. And the only place where negative to positive is right here at about 6.49 and change here. I'm actually going to copy all that and store that as a value so I can use it later. There we go. Now I don't have to keep finding it over and over again. There's this other spot over here, but we don't go negative to positive there. We actually just bounce off the x-axis. So it really was just this one spot here at 6 and change. I'm going to call that A on my sort of my paper response as well, just so I don't have to, again, keep writing this number. So because I have multiple critical values, we have this other critical value right here on the graph. That means that to find my absolute min, I need to use the candidates test. I have no choice because there's more than one critical value. So we're going to plug in this critical value that we've already shown is a local min, and we're also going to plug in the endpoints 0 and 18. All of that into my original g function that tells me how much water I've got. Now g of 0 is pretty easy because at time 0 they told us there was 1,200 gallons of water, so we kind of get that one for free. For g of a, I'm going to have to do that 1,200 plus the integral from 0 to a of g prime of t dt. And let me go to the calculator for that piece of it. So we've got 1,200 plus integral 0 to a, which I've already stored in there. And again, I'm using little g for my g prime. So little g t dt comes out to about 525 if we're rounding to the nearest gallon. Or we could go a little bit more, either way. I guess they didn't say round it off, so we'll take it to the full 3 decimals, 242, yep. And then we also wanted to find g of 18. We actually already found that that was approximately 1,310. Now, if this were the min, we'd go a few more decimals at this point, but clearly the min is happening at time A, and that's 525.242 gallons. So they said at what time is the water at a min? So we actually have to give the time, and again, that's going to be A, and that is in units of hours. For this last part of the problem, for time 18, no water is pumped in the tank, but water continues to be removed at the rate of R of t until the tank's empty. K is the time when the tank becomes empty. We want to write but not solve an equation with an integral that can help us find the value of K. All right, so I'm losing water, but I still got that. So I'm just going to figure out basically how much water do I need to lose? Well, at time 18, we had 1,310 gallons of water. So what I want to figure out is if I take the integral of R of t from 18 until this mystery time K, how long is it going to take before this reaches a value of the 1,310 gallons of water that were in the tank at time 18? So this is the equation that we would have to solve if we wanted to find the value of K. Thankfully, we don't actually have to solve it, so we're just going to call it a day on this one.